So this is a continuation of chapter 3. So what I'm going to focus on in this section is first percent composition, and then spend a lot of time on something called empirical formula. So percent composition is how much of each element is in the compound. So if I have potassium dichromate, it's going to be K2Cr2O7. And if you add up all of those, the molar mass is around 294.2 grams per mole. So how much do you have of potassium, chromium, and oxygen? So what you do is take the mass of each one and put it over the total. So since there are 2 potassiums, you will have 78.2, and then you multiply it by 100. Chromium, same thing. You got 2 chromiums. Here you have 7 oxygens. You can put it over the total. So you get around 26.6, 35.4, and 38.1. These should all total up to be 100%. Do realize that if it's like 99.9 or 100.1, that's just a rounding issue for when you do the molar mass of only 1 digit after the decimal. So that is something we're going to use to do what we call a more complicated problem, which is empirical formula problems. So empirical formula is what we call the simplest formula that we have. So if I have a molecule of like glucose, which is C6H12O6, I could reduce that down to CH2O. So it is a calculation that is useful. Actually, the mass spectrometer is what gives us some of this data. So if I put a sample that is a carbon-based molecule into a mass spectrometer, it's going to give me percentages of each one of the elements. Let's say a 55.8 of carbon, 11.6 of hydrogen, and 32.6 of nitrogen. The overall molar mass is 171. You want to find the empirical formula first and then the molecular formula. So the molar mass is of the molecular formula of how it exists in nature is what a molecular formula is. So we are going to assume we have a 100-gram sample, okay? If we assume that, we could easily do this problem. And it's kind of done in 3 steps. So the first step is to take each one of the percentages and put it into grams. Because if I have a 100-gram sample, if I have 55.8% of that, that's going to be 55.8 grams. So the first step is always to convert everything to grams. Then you want to convert things to their respective moles, because in chemistry, everything is based off of the mole. So you're going to use the molar mass of, again, each one of the elements. So carbon is 12, hydrogen is 1, nitrogen is 14. I'm going to take it out 3 digits here. Sometimes you find some issues if you take it down a little too far, you don't get some decent data. So just keep in mind, usually 3 is going to work for most of the calculations you're going to see. So I've now converted everything to moles. And technically speaking, this could be how I write the empirical formula. This is really the relationship, okay? Of carbon is 4.65, hydrogen is 11.6, and nitrogen is 2.32. That's really what those subscripts are. But we don't like decimals. We don't like to deal with that. So we want this last step is always to get something to 1 so that we have whole numbers. So we're going to divide each one of these by the smallest number. So that's going to be, in this case, 2.32. And then you're going to come out to be whole numbers most of the time. If it doesn't come out to be a whole number, then you're going to have to multiply it by a factor to get it to a whole number. But this comes out to be 2, 5, and 1. So it's going to be C2H5N. And I don't care the order you put them in, but generally speaking, carbon comes first, and then hydrogens, and then whatever else you have in that molecule. So this is what you call your empirical formula. Okay, but I want to know the molecular formula. Okay, so the molecular formula is how it exists in nature. Okay, so going back to my example of glucose, C6H12O6 is the formula for glucose. So you're going to take the molecular formulas, molar mass, and you're going to divide it by the empirical formula, molar mass. So I'm going to have what was given in the problem, 171 grams per mole. And then I'm going to take my empirical formulas molar mass. So C carbon, there's 12 is the molar mass. So 2 times that plus 5 plus 14 gets me 43. And this should come out to be a whole number. So that's going to be the factor you multiply your empirical formula by to get your molecular formula. So this comes out to be 4. So I'm going to take C2 and multiply by 4. So it's going to be C8, H20, N4. So that is how it exists in nature. That is the molecular formula. So this is a pretty standard way of doing an empirical formula problem. But I'm going to make it a little bit more complex than that. So we're going to go to this next problem, which is kind of what I call a combustion problem, because you're going to be burning something in oxygen. So I have nicotine contains hydrogen, carbon, hydrogen, and nitrogen. If a 2.5 gram sample is burned in oxygen, and I get 6.78 grams of carbon dioxide, 1.94 grams of water, and 0.32 grams of nitrogen are the products of the combustion, find the percent composition and empirical formula of the nicotine. So this is a pretty complicated problem. So what I'm going to do first is I'm just going to write out the combustion reaction so you can kind of see it. So combustion reactions are going to be all over this class, so you're going to need to be familiar with them. So I'm going to take a schematic, just a general formula, CX, HY, and Z, because I don't know what the superscripts are. I'm burning it in oxygen, so it's going to be plus O2. And then I have produced CO2, water, which are the most common products that you see in a combustion, but then I also produce nitrogen because I do have nitrogen in the nicotine. So I am starting with a 2.5 gram sample of the nicotine, and I get 6.78 grams of the carbon, 1.94 grams of the water, and 0.32 grams of the nitrogen. So I like to write it underneath it just so I have access to it. You don't have to do that, but that's kind of how I do it. So what do I know? Well, I know that the carbon had to go into the carbon dioxide. The hydrogen had to go into the water. The nitrogen then went into the nitrogen. So the tricky part is if you end up with a molecule with oxygen, you've got a really different type of problem that you have to focus on. But this is going to be kind of the setup that you do. So I'm going to look at carbon. I have 6.78 grams of my CO2. I can divide that by its molar mass of CO2, which is 44 grams, which I will get 0.154 moles. But this is of CO2, okay? If I do the same thing to hydrogen, okay, or excuse me, the water, excuse me, that is 18 grams. I get 0.108 moles of water. And then the nitrogen is 0.32 grams. And I'm dividing that by 28 because that's the molar mass of N2. That's the molar mass of N2. So I get 0.0154 moles of N2. So I have to do an additional step that I haven't done before in these types of problems because I have to get it to carbon and hydrogen and nitrogen. So I have to look at the formula and I have to say, okay, well, how many carbons do I have in there versus the carbon dioxide? So I could set up a relationship. I have 1 mole of carbon for every 1 mole of CO2 because I have 1 carbon in that formula. So I have 0.154 moles of carbon. The water is where it points out what I'm getting at here. I essentially have 1 mole of water, but I have 2 hydrogens in that formula. So I really have to take this number and multiply it by 2 to get the moles of hydrogen, okay? And finally, my nitrogen, there are 2 nitrogens in that diatomic molecule of nitrogen. So I end up with 0.0308 moles of nitrogen. So now I have it down to the elements. So this last step is exactly like the previous problem. I just have to divide it by the smallest number. So the smallest number happens to be the nitrogen one. That one is, of course, going to go to 1. And then do the other 2. And I get 5 and I get 7. So my empirical formula is C5H7N. Okay. So that's my empirical formula, but I need to know what the percent composition is of this. Okay, so now you're kind of working backwards, because once you have the empirical formula, that's actually the hardest thing. So I'm going to have 5 carbons, so 5 times 12 plus 7 plus 14 gives me a molar mass of 81 grams per mole. So all I have to do is essentially take 5 times 12 and divide it by 81 to get my percentages. So you end up with about 74% is carbon, 8.6% is hydrogen, and 17.4% is nitrogen in that formula. So really the only additional step that you had to be concerned with here is going to be the fact that you have the products are not just carbon and hydrogen, but they are coming from molecules. You're going to have an additional step that you didn't have before.